So, Mika, you can start, ma.
Yes, sir. A pleasant morning to all. It gives me an immense pleasure to welcome you all to this highly anticipated webinar on fundamentals of wind energy conversion system. We have gathered here to explore, learn, exchange, and a nostalgic ideas that promises to make a sufficient impact in our field. Before we begin the webinar, I would like to take a moment to extend my heartfelt thanks to our principal, Dr. Prem Kumar, and Professor Dr. G. Balaji, Head of the Department of Electrical and Electronics Engineering for their and unwavering support and guidance. Your leadership and vision have been instrumental organizing this event and bringing together. Now extend my welcome gathering to the chief guest of the day, Dr. Zahir Hussain, who accepted our invitation and giving their valuable words. Let us look forward to this session that's filled with insightful discussions. Once again, I welcome you all for this wonderful webinar. Now I call upon M. Deepika Sri, second year Triple E, to deliver her chief guest introduction.
Welcome you all for this webinar. Dr. Zahir Hussain, Assistant Professor, School of Electrical Engineering, VIT Vellore. He started his Doctor of Philosophy in Indian Institute of Technology, Madras, PhD thesis. New algorithms for optical energy extraction and wind speed estimation for wind energy conservation system. Research areas like microgrid, wind energy, power electronics application in power system, sliding mode control, and observation design algorithms, electric drives. Until he were completed his young Osmania University College of Engineering, Hyderabad. Specialization in industrial drives and controls. And he completed his Bachelor of Technology Regional Engineering College, Warangal, Andhra Pradesh. And he got his experience both 15 years of teaching field, 1.5 years of industrial experience as consultant at GE IBC Hyderabad, and 2 years of experience in industries. Cran University, according to publication in several international journals and conference. Thank you. Once again, I welcome you, sir, for this webinar.
Great. Thank you. Thank you very much for providing this opportunity. Sir, can I share my slide now?
Yes, sir, I can proceed, sir.
Yes, sir.
Okay, let me check. Yeah.
So session is recording, sir.
Yes, sir, session is recording. Yes, sir.
Sir, is everything fine? My slide is visible. Am I audible? Everything is
visible,
fine.
sir. It is visible, audible, and visible also, sir. No problem.
Great. Okay. Yeah. Thank you. I'm very much thankful for providing this opportunity. And dear students, as a professor, as a teacher, I am always happy while interacting with the students. So I hope this presentation will give you some delta improvement in your knowledge in the fundamentals of wind energy conversion systems and some basics of wind energy conversion systems. And at any point of time, if you are not clear about the concept, or if you feel any discomfort, any confusion, please raise your hand, and you know that, right? Yeah, you can interrupt me, and you can take my clarification for your doubt. So this is the disclaimer. I want to make it very clear at the starting of the presentation. At any point of time, you can interrupt me for my clarifications. So can I start, students?
Yes, sir, sure, sir. You can start, sir.
Yeah, great. Thank you, sir. Yeah. So the topic is fundamentals of wind energy conversion system on the eve of energy conservation, week or day, whatever you call. And we know that importance of renewable energy systems. Yeah. So we know that importance of renewable energy systems, and uh, among those renewable energy systems, you know that solar PV system, wind energy conversion systems, and biomass. There are many different technologies are there, but now we are focusing on wind energy conversion system because there is an abundant scope to generate power from wind energy conversion systems. So the status of our country in the production of wind energy conversion system is it is the fourth largest in the world and second largest in Asia. And we know that, right? In our Tamil Nadu, so we have plenty of opportunities to generate power using wind energy conversion systems, and mostly in Kanyakumari, Coimbatore belt. So the installed capacity of wind power in India is 41.93 gigawatts. And why we need wind energy conversion system, why it is gaining the more popularity means, it is, we know that India is shining, India is, it requires huge electricity uh, for its development, and at the same time, it's a concern towards the environment pollution, and at the same time, we need to mitigate the consumption of fossil fuels because of so many reasons. So we are focusing, even government also making the policies to encourage the wind energy conversion system installations. And being an electrical engineer, it is our responsibility to choose any one of the renewable energy technologies. And my job is I want to make you to aware of wind energy conversion system. So if you look at this slide, this is what we know about one wind turbine, right? A very interesting view. And the inside of this wind energy conversion system, the important parts are like this. So you will have this wind turbine rotor, and this wind turbine rotor, it converts energy, it transforms the wind energy, kinetic energy stored in the passing wind into mechanical energy. And that mechanical energy, it will impart, it will produce, it will give as input to another energy conversion device. We call it as a generator. And we know that what is the principle of the generator. Generator converts energy from mechanical form to electrical form. And whatever the energy we get from the generator at output port, that energy is unregulated electrical energy. So what is the meaning of unregulated electrical energy means? It is purely based on availability of wind. So we know that wind flow is not constant. It is an intermittent source. So if the source is intermittent, and obviously the energy output also is not constant. And that's what we call unregulated electrical energy. That unregulated electrical energy, you cannot feed directly to our loads. So we need to modulate, we need to regulate that energy according to the specifications of the loads. And for that, we need one power modulating unit. And we know that power modulating units are power electronic converters. So these power electronic converters, they regulate the electrical energy before feeding to the electrical appliances, electrical loads. At the same time, there is one more important subsystem in the wind energy conversion system. It is called storage subsystem, energy storage system. And we know that why we need energy storage system, right? So whenever we have excess wind, availability of wind, when compared to the demand electrical load, then the excess wind energy we will store in energy storage system. And whenever there is a, lack of wind energy, that's what I said, it is an intermittent source, right? So, but still to produce uninterrupted power supply to the load, so we will discharge, we will take energy from the battery and we will feed energy to the electrical appliance. These are all basic concepts. I know that you feel somewhat, but only one thing is I want to make you comfortable to understand before driving into the actual wind energy conversion concept. So this is the basic of wind energy conversion system, main subsystems inside. Now we will see what exactly the technology involved in the energy transformation, energy conversion process. I hope this particular device the structure of the device is, it's a peculiar shape, just it is one object. So if you place this object in any fluid flow, fluid in the sense maybe liquid or air, whatever, gas. So if you place this particular object like this to allow the fluid, to allow the air pass onto the surface of this airfoil, surface of this structure, then what will happen? Just guess, just visualize, just understand. What will happen if you place this shape object in the air? What will happen? So the immediate effect is going to be this. Just observe this. This particular structure, this is called leading edge, initial point. This is called trailing edge, end point. So whenever air comes here, because at the leading point, at leading edge point, because of this obstruction, these air molecules, they divide into two streams. They divide into two streams. One is upper surface stream, another one is lower surface stream. But when you observe the geometry of this structure, at the upper surface, the length of the surface is something more when compared to bottom surface length. So it's mean that if air is dividing into two streams, so this stream should travel more path when compared to this bottom stream. But we have one concept, this is called conservation of mass flow. So what is the meaning of mass flow means? Or mass rate flow means? So whatever the mass of the air it enters here, the same amount of mass will leave from here. This is called conservation of mass rate flow. Means whatever energy, whatever air particles they enter at this point, all the air particles they will reach to this point at the same time. Means the above surface particles and bottom surface particles, again they will meet again at this particular point at trailing edge. So what it's mean? It's mean that these upper surface particles, to cover the more distance, these particles they have to travel with more velocity. Think, understand. The upper surface air particles, they should, to cover the more distance, they should travel with more velocity when compared to this bottom surface air particles. So this is called velocity difference. So whenever you create some velocity difference, obviously the pressure also will change at above the surface and below the surface of this object. And it creates the pressure difference. And we know that there is a relation between pressure and velocity like this. They are inversely proportional, inversely related. So what will happen now? The pressure at above the surface, if you call it as a P1, and the pressure at below the surface, you call it as a P2, then you can say that P1 is less than P2 because V1 is greater than V2. So because of that, now the pressure difference will happen. And this pressure difference will create one aerodynamic force. That aerodynamic force we call lift force. And how that lift force will act? We know that force will act from higher potential to lower potential. And because of that, this particular geometry, this particular object will move. That particular object will be lifted in the air in that direction, vertically upward direction. This is what the science behind in this particular concept. So when you place one structure, when you place one object in this particular geometry, automatically whenever you allow some fluid to pass over this geometry, automatically that particular object will experience some external force. That external force we call lift force. That aerodynamic force we call lift force. And that is what the creation of lift force is very important in the generation of wind energy conversion systems. And I hope you can recollect the same technology, the same concept we use even in aircrafts also. So whatever the wing we use, whatever the wing we design, wings we design for the aircrafts, all these air, all these wings are based on this type of structure. It's an aerodynamically efficiently designed structure. And that structure is called airfoil. So this is the definition for one term that is called airfoil. It's a cross-sectional shape of an object that creates aerodynamic force, that creates one aerodynamic force when a fluid, if you allow to pass over it. Very, very simple shape, but that particular simple shape is revolutionizing entire engineering. That is what the significance of this particular shape. So once you place that, then it will create mass, it will create a pressure difference. And finally, it will generate a lift force. This is very important concept to enter into the wind energy conversion system uh, technology. So once we understand about what is a lift force, now how you can make at micro level whatever the lift force we are getting. So how you can make use of that particular concept to rotate the entire the length of the turbine blade. And that is what you can understand from this particular slide. And this is one aircraft wing, and you see the cross-sectional view of that aircraft wing is airfoil shape. So you can imagine one particular blade, whether it is a wind turbine blade or aircraft blade. It is a stack of these airfoils. One wind turbine blade is a combination of thousands of airfoils like this. And when you place this particular blade in wind, and just now whatever the concept we discussed, so this each airfoil will experience one external force. And we know that what is that external force name? It is called lift force. And because of that lift force, all these airfoils, they, after experiencing their individual lift forces, then the resultant force, the sum of all the individual lift forces, that resultant force will make this turbine blade to rotate or to move down. And when you attach all the wind turbine blades at the hub like this, then it is going to be, it's not going to be a linear motion. It is going to be an angular motion. You see, these are all individual lift forces on each airfoil. So they all act like this, lift forces. And you see the resultant, what is going to happen? The resultant is going to be this entire wind turbine will rotate in anti-clockwise direction like this whenever you allow air to pass over the blades of the wind turbine. This is what magic will happen. The moment you place this wind turbine to face the wind, it will rotate automatically. And what is the meaning of rotation means? It is the mechanical energy. And this particular concept is called conversion of kinetic energy of the wind into the mechanical energy. By the way, what is the meaning of kinetic energy of the wind? We know that whenever wind is in motion, whenever there is some wind flow, it is because of its kinetic energy only. And what is the formula for kinetic energy? It is half mv square. So where v is wind velocity and m is mass of the wind in kilograms. So this is energy formula, energy expression. Then what about power available in the same wind? What is the relation between power and energy? It is the rate of energy is called power. What is the meaning of rate of energy? It's a dW by dt, right? So the meaning of dW means kinetic energy I'm talking about. D by dt of kinetic energy. So what is the formula for the power? It is half m dot. It is m dot. It is not simply mass, it is a rate of mass. It is the rate of mass. It is m dot VW square. This is power of the available in the wind. And now something you should know about this mass flow, rate of mass flow. So the formula for mass flow is, I'm calling this is the rho A and VW. So where rho is called air density. The meaning of air density means how much mass in 1 cubic meter. It is a kg per meter cube, that is called air density. And A is called swept area of the turbine rotor. Means if you have a turbine blade, something like this, when you rotate the turbine blade, it forms like a circle. So the area of this circle, the area where our turbine will sweep, that area is called swept area. And what is the formula for swept area? It is pi r square. It's a normal circle area. And where, what is r means? R is length of the blade. Length of the blade is called R. So that is what area or swept area of the turbine rotor blade. And we know that VW is wind velocity. The units are meter per second. So altogether, the expression for mass flow rate is rho A VW. And now a little bit more you need to understand about the kinetic energy. So energy is available in the flowing wind. Now I want to convert this energy into mechanical energy. So we know that according to energy conversion principle, you cannot create new mechanical energy, right? So only one thing is you have to extract the energy which is in the form of kinetic energy into mechanical energy. You have to extract. So in this extraction process, kinetic energy will reduce and that will contribute for the generation of the mechanical energy, for the creation of the mechanical energy. So that is what wind turbine job. So that wind turbine transforms the wind power into mechanical power by reducing the kinetic energy. Now this is very important point you should understand. Wind turbine cannot transform entire available kinetic energy in the wind into mechanical energy. Can anyone answer this question, students? Why a wind turbine cannot transform entire kinetic energy available in the wind into mechanical energy? Can anyone, students, just make it more interactive if possible? Students, Okay.
Students, if any doubts, ask the questions to sir.
Students, my question is, this wind is having some kinetic energy, and this turbine is extracting that kinetic energy into mechanical energy. It is transforming this kinetic energy into mechanical energy. In this process, this wind turbine cannot extract entire kinetic energy to transform into mechanical energy. The 100% energy transformation is not possible. Why? That is the question. Can anyone answer this?
So because they have some losses.
Uh, because they have some losses in the energy transformation, and we call it is efficiency, correct? This is one option.
Yes.
Another important option is there. Can you think? So if you in the transformation process, if you make kinetic energy zero, what is the meaning of making kinetic energy zero means? Just normal thinking, common sense thinking. So if you make kinetic energy of the flowing wind to zero, what it's mean? Can anyone? Kinetic energy is because of the wind velocity of that object. So to extract the entire kinetic energy or to make the kinetic energy to zero, you should make the wind velocity to zero. What is the meaning of making wind velocity zero means? Once this flowing air, after passing through the blade, if this turbine extracts 100% of kinetic energy, then whatever the wind reaches to this other side of the turbine, it cannot move, it cannot flow further. It cannot flow further means its wind velocity is zero. Just imagine if you don't make wind to move away from the wind turbine, then you cannot allow fresh wind into the wind turbine. So it's mean that there should be some velocity for the exhaust wind, outlet wind. So if you want to leave some wind velocity at the outlet wind, it's mean that that wind should have some energy. It should retain some kinetic energy. Then only that wind will go out of wind energy conversion system. So this is what the main concept. If you have a wind turbine, you cannot transform entire kinetic energy available in the wind into mechanical energy. So this is very important point everyone should understand. So why the efficiency of the wind turbine is very much low? It is because of this concept. And that's why the expression for power, you know, this is expression for power available in the wind 1 by 2 m dot VW square. And we know that m dot is rho a VW. If you substitute this rho a VW in this expression, then it is going to be 1 by 2 rho a VW cube. And that expression is entire power available in the wind. But we cannot extract the entire power. So there is a one more term we will use here. The term is called CP. So CP is nothing but coefficient of power. This is the expression for wind turbine output power. Wind turbine input power is, what is wind turbine input power? It is 1 by 2 rho a V cube. This is input power and this is output power. What is the difference? The difference is inclusion of this term. It is called coefficient of power. And what exactly the significance of coefficient of power means? Because of the energy transformation concept, you cannot transform entire energy into output side. That particular phenomenon will be represented by this term. It is called coefficient of power. How efficiently the turbine is transforming or extracting the energy from the wind to convert into mechanical energy. So something you should understand more about the term CP, coefficient of power. It is the ratio of wind turbine output power by wind turbine input power. So there are few concepts. It is a derivation by using the axial induction factor. Alpha is called axial induction factor. But in the introduction lecture, I'm not going to discuss on this alpha term. But just remember, there is a term, it is called CP, coefficient of power. And the maximum value of that coefficient of power is 0.593. Maximum value for that coefficient of power or power coefficient is 0.593. Sometimes we call 59.3%. So just now you understand what is the meaning of 59.3%. Whatever the input power available in the wind, only 59.3% of the power only we are extracting into output power. Only that is again maximum you can extract only up to 59.3. Please understand my statement. Maximum power you can extract from the input power is only 59.3%. It is a maximum power. When it is possible maximum power means it is called ideal case. So if your design is perfect, means the blade design is perfect, and if there is no aerodynamic disturbances, then only you can extract the maximum power. And how much that maximum power you can extract means only 59.3% only. So this particular phenomenon is called, that limitation is called Betz limit. So this is very important concept in wind energy conversion system to mention why wind energy conversion system cannot extract 100% of energy from the wind. Why it can extract only maximum 59.3 only. Why you cannot go beyond 59.3% means this is what the entire derivation. And this derivation will come under the title of Betz limit. I hope it is clear now. This concept is called coefficient of power. So after understanding these basics, the expression for coefficient of power, there is one mathematical equation. That coefficient of power is a function of two different terms. One is called tip speed ratio, another one is called pitch angle. So coefficient of power is the function of tip speed ratio. We call TSR. Another one, pitch angle. We call we indicate with beta. So this particular concept, this particular expression will give you the value of CP. And it is a function of, as I mentioned, tip speed ratio and pitch angle. Now the question is, what is this tip speed ratio? What is this pitch angle? Tip speed ratio, it is a ratio of, see, when you allow the wind in this direction, the turbine will rotate something like this, angular rotation. So if you take the tangential direction of that rotating blade, and that tangential direction wind velocity, the tangential direction speed of the tip of the blade, the expression is omega r into r. I'm repeating again, the tangential velocity of the tip of the blade. I'm not talking about angular velocity. I'm talking about tangential velocity. The tangential velocity expression is omega r into r. By the way, what is omega r? Omega r is nothing but angular speed. Angular speed of the wind turbine is omega r. And what is r? R is nothing but length of the blade. So the product of omega r into r will give you the tangential speed of the tip of the blade. Tip of the blade. And divided by wind velocity. The ratio of these two terms will give you the TSR, tip speed ratio. This is very, very important concept in wind energy conversion systems. So you have to visualize this. You have to understand this. What is tip speed ratio? So once you understand this tip speed ratio, then what is pitch angle? So this is wind turbine. This is called hub, and these are wind turbine blades. They are attached like this. And you can see here this arrangement. At this arrangement, you can use a motor. This is our electric motor. This electric motor we can use to rotate this particular blade structure. You can rotate. Rotation means not like our wind turbine rotation. It is a revolution. So you can make that blade to rotate like that. Only in this direction I'm talking about. In this direction. I'm not talking about in this direction. So if you rotate like this, then you can change the angle of that blade. That angle is called pitch angle. And to pitch, to rotate, to change the pitch angle of any wind turbine blade, we install, you see, it's a pitch drive motor. Okay. So just try to understand what is the meaning of pitch angle. So once you clear about these two, then these are the mathematical expressions so far we discussed to model a wind turbine, wind energy conversion system. What is this? This is power available in the wind. And what is this? This is power extracted by the wind turbine. And what is this? This is expression, mathematical expression for coefficient of power. It is the function of tip speed ratio and pitch angle. And what is tip speed ratio? It is the ratio of the tangential velocity of the tip of the blade with the wind velocity. So these are very important mathematical equations, modeling equations, if you want to simulate, if you want to work on a wind turbine. And there is a relation, if you can plot relation between CP versus TSR. That relation is going to be like this. You see, first it will increase, CP value will rise, CP value will increase along with the tip, along with TSR, and it will reach to one maximum value. And if you further increase the TSR, CP will decrease. This is what very peculiar behavior of wind turbine. So CP, what is the meaning of CP? How effectively, efficiently you are transforming energy, converting the energy. That efficiency will reach to maximum value only at one particular TSR. So once you go beyond the TSR, then CP value will decrease. So the value at which you will get maximum CP, that TSR is called optimal TSR. We know that, right? It's a normal optimization theory. It is called optimal TSR. So from the CP versus TSR, you should know there is a CP max value and there is one lambda optimal value. This one you should understand from the CP versus TSR relations. So once you understand this, then look at this interesting concept. This is called mechanical power output versus turbine speed relation. The characteristics of the wind turbine. Characteristics of the wind turbine, relation between turbine output power and turbine rotor speed. Students, please understand what is the meaning of rotor speed. Rotor speed means if this is the wind turbine rotor, this is what rotor speed. How many rotations it is making in 1 minute or in 1 second. In 1 minute means we call it as RPM, right? So that is what rotor speed. And there is a relation between rotor speed and output power of the turbine. Output power of the turbine means that is going to be input power to the generator. And what is that relation? Means you look at this first curve. This particular curve is at one particular wind velocity, 4 meters per second. Just try to understand what is the meaning of this. So if wind flows like this with a velocity of 4 meters per second, so by changing the rotation, by changing the RPM of the turbine rotor, you can control the output power of the turbine. That is what the point you need to understand from this characteristic. I'm repeating again. If wind velocity is 4 meters per second, then if you control, understand that word is very important. If you control the speed of the rotation speed of the turbine, if you control this rotating speed of the turbine, then output power will change like this. If you rotate the turbine at 100 RPM, output power is going to be only this much. If you rotate the turbine at 200 RPM, the output power is 180 watts. If you rotate the turbine at 300 RPM, the output power is going to be just like 80 watts. But wind velocity remains same. That is the point you need to understand. So only one thing you need to understand is in 4 meters per second wind speed, if you control the rotor, if you control the turbine speed at 200 RPM, then you can extract maximum power, that is 180 watts. You should control the speed of the turbine rotor. So just look at one more. So what is this another characteristic? This characteristic is when wind velocity is 5 meters per second. So just try to understand what is the meaning of this. So if wind flows with 5 meters per second, if you control the rotating speed of the turbine, instead of 200, if you control at 260, if you rotate the turbine with a speed of 260 RPM, then you can extract maximum power. How much that maximum power? 300 watts. So how to control the speed of the turbine? That is next concept. So don't think that turbine speed will not be under our control. No, that is not correct. So whenever wind speed increases, definitely turbine rotation speed also will increase. But you can control the rotating speed by using the power electronic converters. So by using power electronic converters, you can control the speed of the turbine. By controlling the speed of the turbine at one particular speed for a given wind velocity, you can get maximum output power. So you have to operate wind turbine only at that particular speed. You see one more wind velocity at another wind velocity, at another wind velocity. What is that last wind velocity? It is at 8 meters per second. So what it's mean? If wind flows with 8 meters per second with more kinetic energy, then if you control the speed, of the turbine rotor at 410 RPM, then you can get maximum mechanical power from the wind. You can extract maximum power from the wind. How much that maximum power according to this simulation? 1100 watts. These are all very important characteristics, very important concepts of one wind turbine. So for each wind speed, there is one optimal rotor speed. It's a one-to-one relation. So whenever wind velocity changes from 5 meters per second to 6 meters per second, then you should control the speed of the turbine to extract maximum power from the wind. So this point is very important point. That point will lead to the concept of maximum power point tracking. Okay. So look at this. This is one hardware experimental setup. The experiment setup name is wind turbine simulator. What is the meaning of wind turbine simulator? To perform experiments, to conduct research on wind energy conversion systems, you cannot conduct research on real wind turbines, because when you conduct research on real wind turbine, the incoming wind is not in our control. So to conduct research on wind energy conversion system, you have to control you require constant wind speed for certain amount of time. Then only you can do some research. Then only you can propose the algorithms for that particular wind velocity. So the point is, whenever you want to perform any research or any experiment on renewable energy sources, so we don't do that research in real field. So you need to create one laboratory experimental setup to simulate, to mimic the characteristics of real wind turbine. So that particular setup is called simulator. And this is what wind turbine simulator. So this wind turbine simulator will have two main concepts. One is motor generator set. Motor generator set. Next, power electronic converter. Next, electrical load. Next, controller. So you can call it is a microcontroller or DSP controller, whatever you call. So, and this is called host system. So what is the meaning of host system means? In this host system, we will simulate the turbine. We will develop the code, control algorithm code we will develop. And that code will run on this controller. Control algorithm code will run on this DSP controller. So if you run the DSP algorithm, control algorithm on DSP controller, it generates control signals. It generates gate signals. Those gate signals you will feed to this converter, power electronic converter. And that power electronic converter will control the output of the power electronic converter, that is going to be the input to the motor. So what it's mean is to control the speed, to control the behavior of this motor, you need to control the polytronic converter gate sequence, pulse sequence, control gate pulses sequence. So to generate those control gate pulses, we use one DSP controller. To develop program for this DSP controller, we use one system, host system we call it is. So by controlling this motor, why we are controlling this motor means this motor will act as a wind turbine rotor. It behaves as if it is a real wind turbine. It performs, it behaves this type of characteristics. It gives this type of characteristics. To obtain these characteristics, you should control that motor by using one polytronic converter. So as if you have a wind turbine like this, behavior of this electrical DC motor is as same as one wind turbine. That wind turbine shaft you are coupling to the generator, right? So it is nothing but this is PMSG generator, permanent magnet synchronous generator coupled to one DC shunt motor. This is DC shunt motor. DC shunt motor main objective is to mimic the behavior of the wind turbine rotor, and the wind turbine rotor output you are feeding to the generator. It is called PMSG generator. And output of the PMSG generator we are feeding to this electrical load. So this is what the setup, experimental setup we developed in our laboratory to simulate the behavior of the wind turbine. But directly working on wind turbine on hardware is not advisable. So first we need to simulate the behavior of the wind turbine by generating the different control signals, and we should verify the performance of the wind energy conversion systems through simulations. And for that purpose, we need to develop simulation models. So this particular window will show you the experimental results of that wind turbine simulator. Just now we have seen, right, at different wind velocities, how the speed versus power characteristics. So these are the results of the hardware experimental setup. So like I said just now, so you should not start directly working with hardware. You have to work with simulation studies first. And for that purpose, we need to create a simulation model. And that particular simulation model should implement one concept. It is called MPPT algorithm. That operation is called MPPT operation. What is the meaning of MPPT? It is maximum power point tracking operation.
Tracking
Correct.
system.
So to extract maximum power from the wind, what is the meaning of extracting maximum power from the wind means if wind velocity is 8 meters per second, then you should operate the wind turbine at this speed. Then only you can get maximum power. If wind velocity changes to 6 meters per second, then you should operate the wind turbine rotor at this speed. Then only you can get maximum power from the wind turbine. This process is called maximum power point tracking operation. So to perform this activity, you should develop one control algorithm. That control algorithm you can develop by using simulation studies first. So if at all you want to, you see this is one wind energy conversion system. Whatever we discussed just now, we have a wind turbine rotor, and the turbine rotor is coupled to a generator. And it takes mechanical input and gives electrical output. That electrical output we are feeding to power electronic converter, and output of the power electronic converter, it will go to the electrical loads and to the storage systems. And here the concept is how you can control the speed of the rotor. To control the speed of the rotor, we have the expression, it is omega m is equal to Tm minus Tg by B. What is the meaning of Tm? It is the torque given by the turbine. That is called mechanical torque, output torque of the turbine rotor. And what is Tg? It is the opposition torque. Yes, it is opposition torque given by the generator. Generator always will oppose the input torque. And how to control the generator torque means this is the relation. By controlling the current passing through the generator windings, that is called, I am calling Ig. By controlling the current passing through the generator stator windings, you can control the generator torque. By controlling the generator torque, you can control this numerator. You can change this numerator. And by changing that numerator, you can control the turbine rotating speed. Again, the same question. Why we need to control the turbine rotating speed? It is to operate the rotor at optimal speed. Then only you can extract maximum power. So the point in maximum power point tracking means you should control the generator torque. To control the generator torque, you have to control this current through the windings. To control the current through the windings, we will use power electronic converter. And we know that power electronic converter will have semiconductor switches. Every power electronic conductor will have semiconductor switches. And every switch, it needs its own gating pulse. And those gating pulses we have to provide. By providing the gating pulses, you can regulate the power electronic converter. Then who will provide the gating pulses? Our control unit will provide the gating pulses. Our control unit means our DSP processor, microcontroller unit. This is what the overall idea of one wind energy conversion system for MPPT operation. There are different algorithms are available in the literature for maximum power point tracking. And where that maximum power point tracking algorithm will come means in this block diagram, here it is. This algorithm, maximum power point tracking algorithm, will take the feedback signal, what is wind velocity, what is the present speed of the turbine. How you can give wind velocity means by using one anemometer. Anemometer we know, right? So it will measure the wind speed. So it feeds the wind's velocity information into this algorithm, and algorithm will take the rotating speed, present speed. Based on these two informations, it will generate the appropriate control signals. Those signals will go into the power electronic converter. The design of this block is very, very important. That is what, as a researcher, as a student, you have to work on this. How to propose, how to develop, how to design a new MPPT algorithm, and how to implement that MPPT algorithm by using one suitable control system. So as I said, there are many MPPT algorithms are available in the literature, but conventionally, these three are very important algorithms. One is tip speed ratio algorithm. Another one is power signal feedback algorithm. Third one is hill climb search algorithm. These are very conventional, popular algorithms. And nowadays, people are going with ML-based algorithms, hybrid algorithms, adaptive algorithms. Okay, these are. all these algorithms are derived from this conventional algorithm, primary algorithms only. So you should start your journey with these algorithms. What is TSR algorithm? What is PSF algorithm? And what is HCS algorithm? So one more information you should know, the generators, the type of generators in the wind energy conversion systems, you can find with a different topology. So few wind turbines will be with permanent magnet synchronous generators. Few wind turbines with doubly fed induction generators, and very old wind turbines, they are with induction generators. Most of the small power rating turbines are with PMSG generator. High power rating wind turbines are DFIG based generators. So nowadays we are not using induction generators. It is almost obsolete. So understand, DFIG based wind energy conversion system or PMSG based wind energy conversion systems like this. You have to understand. So now to implement one MPPT algorithm on a DFIG based wind energy conversion system. So this is the block diagram. So what this block diagram says means, you see, this is our turbine rotor connected to the generator. Generator is DFIG generator, doubly fed induction generator. It will have stator and rotor. Stator winding you can connect directly to the grid, but rotor winding you will connect to the grid through two converters. They are called rotor side converter and grid side converter. These are called back-to-back converters in rotor circuit. They are coupled, they are connected with a DC link. So this is power circuit, main circuit of our wind energy conversion system, DFIG based. But to control these two power electronic converters, you need to design one control system for the implementation of maximum power point tracking algorithm. And what is that control system means? This is that control system, remaining part. And here, the first thing is our MPPT algorithm. As I mentioned, MPPT algorithm will take few things at input as feedback signals. Then it generates, after analyzing, after implementing one algorithm, it will generate reference signal for the generator. Reference signal for the generator. We know what is the meaning of reference signal for the generator from the control system point of view. So we should maintain this speed in the generator. For that purpose, we will compare with the actual speed, present speed, and whatever that mismatch we have, that error signal we feed to the PI controllers. And from the PI controllers, there are two controllers we use: inner current controller, outer speed controller, inner torque controller, outer speed controller. There are two PI controllers. By using those two PI controllers, you can generate finally the reference signal for the stator winding. And that reference signal for the stator winding, we will perform the space vector modulation technique to generate the control signals for the converters. These control signals we will feed to the converters. So this is the simple view of a block diagram for a DFIG based wind energy conversion system with MPPT implementation. I'm not expecting the entire things you should know at this stage, but my objective is to make you aware of what is the main system, what is control system, and what are the main important components in the control system. So that is what my objective. And that's why I explained in brief. So what are the things you should have in a block diagram of a DFIG based wind turbine? So that particular concept you can implement on a MATLAB model. So this is a MATLAB model. In this MATLAB model, you see, first of all, wind turbine. Wind turbine, whatever the mathematical modeling equations we developed. What are the mathematical equations we developed? 1 by 2 rho pi r square v cube Cp. This mathematical equation where Cp is the function of lambda and beta. These mathematical equations you have to implement in MATLAB. Okay, so let me share my model. Here it is. Students, can you able to see my model on MATLAB?
Yes, sir. Visible, sir.
Yeah, that's right. So this is the same model what I projected on slide. So this is what I said, wind turbine model simulation equations, mathematical equations. So if you double click on this, if you open this, it will open the subsystem. In this subsystem, you can see the implementation of all those equations, CP implementation, PM implementation, calculation of TSR, all the things you have to, it's a normal, just only one thing is you should know the mathematical modeling equation and in your own way you can implement, right? You have different approaches to implement any equation in Simulink or MATLAB. So you can follow your own way. So finally, you have to make that subsystem to give the output of torque. First, you will get power, and you know the relation between power and torque, and you will get the torque output from the wind turbine block. And that torque output, where it is here, that torque output we will feed to the generator. This is called generator. And as I said, this is our W-fed induction generator. This W-fed induction generator will have stator winding and rotor winding. This capital ABC, I don't know whether it is visible to you or not, but that capital ABC stator winding terminals and this side small ABCs, they are rotor winding terminals. As I said, stator winding terminals are connected directly to the grid. This is grid. Similarly, rotor winding terminals are connected to back-to-back converters. This is called our rotor side converter. This is grid side converter, and this is DC link. And the grid side converter is connected to the grid again. So what is polytonic converter? If you open that RSC, rotor side converter, there you know how to implement, how to design one polytonic converter on Simulink. So you can take this block, universal bridge block. You can give, this is rotor side converter implementation. And similarly, another one is grid side converter implementation. And how to generate the control pulses to these converters. And for that purpose, this is another block, right? To implement rotor, to generate pulses for the rotor side converter, this is rotor side control block. Similarly, to generate control signals to the grid side converter, you should have one more control block, control subsystem for grid side converter control signals generation. So like this, you will have two different subsystems for rotor side converter control and grid side converter control. So if I open this rotor side converter control, these are the main blocks inside that rotor side converter. You know, as I said, you'll have two controllers, PI controllers. One is inner current controller, another one is outer speed controller. inner torque controller, outer speed controller. And after that, implementations, transformations from the rotating frame to stationary frame, DQ transformations. And we know that what is the importance of DQ transformations? It is to avoid the change in the inductance value, to change in the mutual inductance value. So everything, it should appear like a stationary thing. There should not be any rotating thing. Relatively, I'm talking about relatively. So we know that that is what the objective of the transformations. After knowing the rotor position, you can implement these transformations. Rotor position is required for the implementation of the transformations from rotating frame to the stationary frame. And by using those transformations, you can generate, that's what I said, it is pulse width modulation technique. Okay. Some people, they implement space vector modulation, and few people, they implement simply sinusoidal pulse width modulation. It is up to you. Based on the specifications, based on the performance, you can decide. Implement and generate the appropriate control signals for both the RSC and GSC, rotor side converter and grid side converter, so that you can control the power extraction. You see here, this is the block. To control this speed, here I have implemented TSR algorithm. And what is the input for the TSR algorithm means wind velocity. So take the TSR algorithm, implement the TSR algorithm in this block, so that this block will generate the reference signal for the speed, that is called speed reference. And with that speed reference, our internal subsystem of rotor side converter, you have to design, you have to implement. If I get opportunity next time, how to design the algorithm, how to develop the model, definitely I'll be very happy to share that information with all of you. But this particular discussion will confine only to the introduction level. So like this, you can develop the control system subsystem, control blocks for rotor side converter control. Similarly, for grid side converter control. So that's what we are back here. So once we implement that, then once you run the simulation, so this is going to be the output. If you look at the simulation model, here these are the different inputs I am feeding to the scope block. First one is wind velocity. And what is wind velocity? Wind velocity I'm feeding here. This is wind velocity and this is wind velocity. And if I open the signal builder, this is the way I am changing the wind velocity randomly. For the duration of 10 seconds, you see, initially I made wind velocity 8 meters per second from 0 to 1.5 seconds. Then I changed the wind velocity from 8 to 9.2. Then I made the wind velocity constant up to 2 seconds. Then at 2 seconds, I changed the wind velocity to 10 meters per second. I maintained 10 meters per second for the duration of 1 second from 2 to 3. Like that, I changed the wind velocity input. This is what the case no in our wind turbine. Wind velocity is not in our control. It will change randomly. So that type of behavior you can emulate, you can simulate, you can give by using the signal builder block. By changing the wind velocity stepwise, you can change linearly also. You can change in any manner if you want. Use this signal builder block. Give all the design the shape of the wind velocity profile. Then feed that shape to the simulation model. Okay, and that is what here you can see in the results. The first one is that wind velocity. And what is the second one? Second one is, if you look at this second one, in the scope. Second one is omega reference and omega m. Means how exactly your control system is tracking the reference speed. Right? You see, wind velocity is 8 meters, 10 meters, but reference speed is 500 RPM, right? 1000 RPM, 1500 RPM. Like that, reference speed is changing. Whenever there is a change in the reference speed, how you are generating this reference speed? By using MPPT algorithm. Your MPPT algorithm will generate the reference speed. That reference speed you should track. And this is what even tracking also you can see here. Actually, here you have two plots. One is reference speed, another one is actual speed. Right? You can understand here. You see, for the second input to this simulation block, scope block, I'm feeding two signals, omega reference and omega m. And from this plot, you can say that my system is exactly tracking the reference speed. What will happen if you track the reference speed? If you track the reference speed, your system will operate at maximum power point always. Even though wind velocity changes like this, but always system will operate at maximum power point. How you can say system is operating at maximum power point means you have to monitor the value of CP. And that is what this third plot. So CP is continuously, it is at 0.42. You can see this value. Why CP is at 0.42 means in my system, if you see CP versus TSR, I'm talking about this CP versus TSR, that value is that 0.47. So maximum CP value, my system will go up to how much means 0.47. And that is what here I'm getting that 0.47 in this simulation. This is 0.47, not 42, it is 0.47. Okay. And this is the way you can, this is the proof. You can say that whether your system is operating at maximum point or not. And what is the third one? Third one is TSR value. This is, yeah. This is TSR value. We are exactly maintaining TSR value at 7.2 something. This is the optimal TSR. And these are all, this is DC link voltage. This is the speed of the generator, right? And this is the torque of the generator. And this is generator output. This is generator output. So like this, you can simulate the system, you can inspect all the plots, and so that you can say that once you verify your CP is maintaining at its maximum value, then you can say that, yes, my system is working fine. So now I can go for hardware implementation. With that conclusion, now you can shift from simulation studies to hardware system implementation. So like this, you can design, you can work, you can perform research activities on wind energy conversion system in your laboratory. So these are the few publications based on my work, and I'll be very happy if you have any queries to ask. Students, that's what.
Anybody, please ask to
Yes,
Professor,
sir.
sir.
Yeah.
Sweet for noon, sir.
Sorry, Mike can ask.
Sir, what are the key factors to consider when selecting a wind turbine for a specific site?
It is a purely based on availability of the resources. Simple. Why
Okay,
we
sir.
are installing thermal plant at somewhere else, thermal power generating plant? Actually, we need power at load center, but we are generating the power at remote places, hundreds of kilometers away. Even hydro plants also. It is purely based on availability of the resource. So if you want to install a wind turbine, and if you want to decide the power rating of the wind turbine, you should study the availability of the wind. If you have plenty of wind available, like a Kanyakumari belt, yes, you can go for very high power rating wind turbines, you can go. But even on our rooftop also, you can install a wind turbine, but not that much power rating. It is only just 500 watts wind turbine you can install on your rooftop, because the availability of the wind is very much less. That's why. So answer
Okay,
to
sir.
your question is, you have to check, you have to see the history of the wind profile. Then you can decide. That is a key factor in selecting the location of the wind energy conversion system site. Yeah.
Thank you, sir.
Yes.
Good afternoon, sir.
Yes.
So, whether any software will suit for design and planning for a wind farms projects?
For wind farm, actually, there are few power flow, and there are few softwares are available really. But yeah, Homer is one available software. HOMER. You can note down that. So this is a NASA related website, NREL. So you can make use of that website. It's a free version. You can design, you can decide. Okay. It's a
Okay.
HOMER, Homer. Yeah,
Sir, I have one more question.
please.
Sir, any other methods of estimating the wind energy potential?
Yeah, there are many methods are available. For potential, no, you need first measurements. Okay.
Okay, sir.
So
Okay, sir.
there are estimation methods are there, but finally you should compare with the real measured value. For that purpose, first you have to measure. Then you can perform optimization methods, statistical methods to estimate the availability of the wind. Yes, there are few methods are available, statistical based methods. Correct.
Okay,
But
sir. Thank you,
those
sir.
methods can predict. With that prediction, you can control the generator speed. For that purpose, you can use those algorithms, not for choosing the site. Yeah.
Sir, whether in insisting the designs of the machine?
Design of the mission, yes, you can go for custom made, but generally we don't go. We use only one thumb rule. For low power rating, means below 5 kW, even you can go up to 10 kW. Better you go with PMSG generator. And after that, in above 10 kW up to megawatts range, you can go with DFIG based wind turbine. You're talking about generator selection point of view only, right? Am I clear?
Yeah, yes. Yes, sir. Yes.
You can use these two rules to decide whether PMSG or DFIG. But when I say PMSG, controlling is very easy because it is small power rating, and you have to control only one power electronic controller, but it is a full power controller connected in stator circuit. But when you move to DFIG, there you should control two power electronic converters. And those rating of the power electronic converters are only 30% rating of the entire wind turbine system. So because of that, we prefer DFIG based control for high power rating missions, high power rating wind turbines. I hope it is clear, right?
Yes, sir. It's clear. Thank you.
Great, thank you.
Sir, I have one more question, sir.
Please.
How can I get a wind turbine or wind farm at my house or property, sir?
Okay, what about wind is available at your place, first of all?
No, sir.
Yeah, that is a problem, no? Then why you want to get wind farm at your place, right?
Yes, sir.
So yeah, if you have sufficient wind at your place, then directly you can approach the government, central government schemes are there, MNRE website, right? There you can get the entire information. But my advice is, my suggestion is, if you are really interested to generate power, first you install one small 500 watts wind turbine on your rooftop. That is
Yes,
better.
sir.
Yeah,
Okay, sir.
right.
Thank you, sir.
There are two different turbines
Example,
are
sir.
there.
Any
Horizontal
question is
axis
there?
wind
Sir?
turbine. Only one information, sir, I want to share with my students.
Okay, sir.
Yeah.
Yes.
So
Add
there are
it in,
two
sir.
types, horizontal axis wind turbine and vertical axis wind turbine. Just note down these two. And if you are really interested, just browse what about these two. Conventional wind turbine, majority of the wind turbines are horizontal axis wind turbine. But nowadays, even vertical axis wind turbines are also they are getting their own popularity, and we will use this at small power rating. Vertical axis wind turbine I'm talking about. Just for your homework, note down these two missions and browse, find out, and then you can go which one is you are interested. Thank you. Yes, sir.
Participants, any other question is there in your side? Sir, shall we wind up the session, sir?
Yes, sir. From my side, first of all, I'm really thankful, sir, for giving this opportunity.
So, so we can start now.
Now I call upon N. Nagavashita, second year EEE, to deliver her vote of thanks.
On behalf of this webinar organization, I would like to extend my heartfelt gratitude to all of you for joining us today for this insightful and engaging webinar. I express my sincere thanks to our esteemed speaker, Dr. Jahir Hussain sir, for sharing his valuable time, expertise, and knowledge with us. Your insights and practical takeaway have not only enlightened us, but also inspired us. Thank you, sir.
Yeah, thank you.
Really, once again, thank you, sir. You can spend your valuable time with us. The session is more valuable and enhance your wind energy concept and basic knowledge of students. Thank you so much, sir, once again.
Right. Thank you very much, sir,
Thanks.
for giving this wonderful opportunity. Thank you very much. Bye, sir. Bye. See you.